Welcome back, and today we are starting Chapter 4, Section 5, Triangle Congruence, using SSS and SAS. Try these questions, come back and check your work. So we haven't been given a diagram. We're just asked to name an angle formed by two rays. They both have the same endpoint though, right? So we could say that, we could draw that, and we could say that the angle could be angle A. It could also be angle BAC or CAB, right? Three sides of angle ABC, or triangle ABC, and all pairs of congruent and corresponding parts would be angles and segments. There you go. Good. Today we're going to apply SSS and SAS to construct triangles and solve problems. We're going to prove triangles congruent by SSS and SAS. So there's a property that gives you a shortcut for proving two triangles are congruent. It says that if the side lengths of a triangle are given, the triangle can have only one shape. It's a property of triangle rigidity. Remember that before when we were talking about transformations, right? So rigidity means congruent, right? Clones. Same size, same shape, but maybe they have a different orientation on the coordinate plane. This postulate is called side, side, side. Notice that these two triangles have sides that are of the same length. Triangle ABC is oriented differently in space than triangle FDE, right? ABC is congruent to triangle FDE because we know that if three sides of one triangle are congruent to three sides of another triangle, then guess what? The triangles are congruent, which means what? Yes, all angles, all corresponding angles are congruent. So adjacent triangles, if we have triangles that are adjacent, they share a what? That's right, a side. It's like adjacent rays share a, adjacent angles share a ray, right? So you can apply the reflexive property to get a pair of congruent parts. So notice in this set of triangles, triangle ABC is congruent to triangle DBC. We know that BD is congruent to BA, right? We know that AC is congruent to CD, and with the reflexive property, we know that the third side of each of these triangles is the same. Therefore, the third side are congruent, right? So we can say that triangle ABC is congruent to triangle DBC by SSS. An angle formed by two adjacent sides of a polygon, so here we have AB and side BC, they have this angle that is formed between them, right? We say that angle is called an included. It's included inside of these segments, okay, an included angle. So angle B is the included angle between sides AB and BC. All right, so the second postulate for today says that if two sides and the included angle of one triangle are congruent to two sides and the included angle of another triangle, then we can say that these two triangles are entirely congruent. This is called side, angle, side, SAS. It's like a little sandwich, SAS, with an A in the middle. The letters SAS are written in that order because the congruent angles must be between the pairs of congruent corresponding sides. I guess we could say this with a singular, right? The congruent angle must be between the pairs of congruent corresponding sides. So this diagram shows part of the support structure for a tower. Let's use SAS to explain why X, Y, Z is congruent to V, W, Z. All right, so we already know that side VZ is congruent to side ZX, right? Actually, let's start with the sentence they gave us. We know that XY xy, oh, we don't know that. We don't know that xy is congruent to wv right off the bat, do we? So we move to the next segment. yz is congruent to wz because that's given, right? And we know that zx is congruent to zv because it's given. And then what do we know about this angle here that's between these two given sides? Well, we know it's a vertical angle with this angle here, right? So xzy is congruent to wzv. We can use a little mark to show that. We know that these are vertical angles, so they must be congruent. So now we can see that x, y, z must be congruent to v, w, z based on SAS, right? SAS. And you can follow their reasoning here. Let's use SAS to explain why these triangles are congruent. Okay, we know that side AB is congruent to side BD, it's given. We also know that angle DBC is congruent to angle ABC, right? That's given. So we have side angle, and we can say that BC is congruent to itself, right? BC is congruent to BC. BC forms a side of each of these triangles, and that is based on what? That's right, the reflexive property of congruency. So we could put little dashes there, I suppose. This side is congruent to itself. And so we can say by SAS, that these two triangles are entirely congruent. So the SAS postulate guarantees that if you are given the lengths of two sides and the measure of the included angle, you can construct one and only one triangle. So all you need to know are two sides and the included angle between those sides, and the third side would have to fall into place based on SAS. So let's show that these triangles are congruent for the given value of the variable. Well, of course, we're going to substitute, right? So PQ, we've been given this expression, x plus 2, right? And so what will we do? We're going to substitute 5 and find that PQ is 7, all right? Which PQ, therefore, is the same length as MN, isn't it? All right? Now we're going to plug in the value of QR. QR, the expression is x, right? And x equals 5, so there we have QR equaling 5. And O equals 5 as well, right? So we have two sides that are the same length as two sides in this triangle. And finally, when we plug in 5 for the PR expression, we would have 15 minus 9, which is 6, right? And so we now have a third side, 6, that is the same, is congruent to this third side, MO. So which postulate could we use to state that these two triangles are congruent? You got it, SSS, right? These triangles are congruent by SSS. Remember, they've got to be named with corresponding vertices. M to N crosses over the side length 7. P, Q does the same. And then we go QR 5 and O 5. Okay, how can we show that these two triangles are congruent given the value of this variable? Well, once again, we'll plug it in, won't we? So you might pause and run through this. If y is 4, we can find ST, right? ST is 2y plus 3. And we plug it in, and we get 2 times 4 plus 3, which is 11. Okay, so we have a side length 11 here, which matches up with WV, right? And now we'll find TU, which has an expression y plus 3. When we substitute, we get 7, which matches up with length WX. So we see that we have 11 with a 92-degree angle and 7. We have 11. What is this angle? Because we do have 7. If we can prove that this angle is 92, we can prove that these triangles are congruent by SAS, right? So let's plug it in. Let's plug 4 into the expression for the angle T, and when we do, we find that that angle does indeed equal 92 degrees. Therefore, we can say these two triangles are congruent by SAS. All right, we're going to prove that triangle ABD is congruent to triangle CDB. So we'll start with what? Our given statement, right? BC is parallel to AD. That's given. If BC is parallel to AD, we might want to say something with that, right? So we could say that angle CBD is congruent to angle CBD is congruent to angle ABD. So let me draw that in. We have this angle here is congruent to this angle here, and that was based on the parallel lines with a transversal, right? So we have, what do we call those? Alternate interior angles. Okay, and we'll probably now state the second bit of given information. BC is congruent to AD. BC is congruent to AD, and we see that that's given. So we now have a side with an angle. Can we take this other side that would include this angle and prove that it is congruent in both of these triangles? Yes, we can, right? We can say BD is congruent to BD, and that, again, is the reflexive property of congruency. So we are ready to say that these triangles are congruent based on which postulate? SAS. Okay, the final proof today. Let's do it. Pause, see if you can do it. Come on back. We'll start with we'll start with QR is congruent to QS. That's given. And now we'll say that QP bisects RQS. Sometimes those are given all in one step, right? So if that is bisecting by definition does what? Yes, it divides an angle into two congruent angles, right? So let's say that next. We can say that RQP is congruent to SQP, definition of a bisector. So now we have we have side and angle. We just need this side, right, to prove these triangles are congruent. So can we say that QP is congruent to QP? Yes, we can. The reason is reflexive property. So we are able to say that these two triangles are congruent based on side, angle, and side postulate. Pause and come back and check your work. Okay, the answers are given. And pause, try your best, and come back and check your work. Okay, and here you go. There you go, have fun.